Welcome all to today's lecture. Myself Assistant Professor Tukur Gupta from Ajay Kumar Garg Engineering College, Ghaziabad. The subject that I am covering in my lecture series is microprocessor. Subject code is KCS 403. Today I will be discussing 8085 timing diagrams. First of all, let us understand what is timing diagram. Timing diagram represents the representation of various control and status signals during the execution of certain instruction. So, it represents the execution time taken by each instruction in a graphical format. So, it is a graphical representation of initiation of read or write signals and transfer of data operations under the control of three status signals. What are the status signals? As I have already discussed earlier, input output oblique memory bar. So, this here the memory portion is the active low signal S1 and S0. So, these are the status signals. So, the various operations which are taking place in the microprocessor under the three status signals, these are represented in a graphical form, and that is known as the timing diagram. The combination of these three status signals identify different operations going on in the system, and how they identify, let us see. So, these are the three status signals and these are the control signals, read, write and INTA bar. The various machine cycles which are represented through the status and control signals are opcode fetch, memory read, memory write, input output read, input output write, acknowledgement of INTR, that is INTA signal, bus idle, acknowledgement of RST or trap, halt and hold. So, these are certain machine cycles. The basic machine cycles that we are going to discuss today are opcode fetch, memory read, memory write, input output read and input output write. The combinations of status signals which represents opcode fetch is input output oblique memory bar should be 0, because this is the memory operation, and S1 and S0 should be 1 1. In case of memory read, S1 and S0 should be 1 and 0 respectively, and since this is the memory operation, so this signal input output oblique memory bar is 0. Similarly, in case of memory write, this input output oblique memory bar is 0 and S1 and S0 is 0 1. So, in this way memory read operation is represented by S1 1 and S0 0, and memory write is represented by the opposite signals. Similarly, when we talk about the control signals, since some reading operation is going on in the first two machine cycles, so this read signal is 0 0, since this is active low, and here some writing operation is going on in the input output write and memory write. So, here the write operation should be 0 to represent the active low write signal. So, in this way the various status and status and control signals represent the different operations taking place in the microprocessor. Other basic terms which are considered while studying the timing diagram is the clock signal. 8085 divides the clock frequency provided at x1 and x2 inputs by 2, which is called operational frequency, that is operating frequency. So, this one cycle represents the one clock cycle, or we say one T state. Ideally it looks like this, but practically there is some error on the rising and the falling edges. So, these rising and falling edges are not straight ideally, that is practically. Now, the single signal status is represented by a line that may have the status either logic 0, 1 or tri-state. So, the lower line represents logic 0, the upper line represents logic 1, and the line like this represents the tri-state signal. The group of signals is represented by these two over the crossing lines, or we can say overlapping lines. This represents the valid state and this represents the tri-state. So, this can be considered as a general machine cycle timing diagram, or we can say a combination of machine cycles. So, here this shows one clock period, this shows the different T states like state 1, state 2, state 3 and so on. Suppose this is machine cycle 1 and this is machine cycle 2. So, the combination of these two machine cycles are making some instruction cycle. This is the leading edge, this is the falling edge. So, we can conclude that T state is this one subdivision of an operation performed in one clock period, and each T state is precisely equal to one clock period. Machine cycle is the time required to complete one operation of accessing memory, input, output, or acknowledging an external request. This machine cycle consists of 3 to 6 T states. The various machine cycles are opcode, fetch, memory read or write, input, read or write, interrupt, acknowledgement, halt or hold, and reset. The instruction cycles means the time required to complete the whole of instruction, and it may be a combination of different machine cycles. So, we can say that machine cycle is the combination of T states and instruction cycle is the combination of various machine cycles. The basic functions of every instruction is fetch and execute, that is opcode, fetch and instruction execute. The number of instructions are stored in the memory in sequence. In normal process of operation, the microprocessor fetches or receives, we can say receives or reads and executes one instruction at a time in the sequence until it executes the halt instruction. So, this is a normal execution of instructions. Thus, an instruction cycle is defined as the time required to fetch and execute an instruction. So, the very basic function which is a part of every instruction is the fetch cycle. First of all, whenever we want to execute certain instruction, first of all it is fetched from the memory. So, fetch machine cycle is the compulsory machine cycle which is present in each and every instruction. So, every instruction is composed of two machine cycles, that is a fetch cycle and execute cycle. So, we can mention that instruction cycle is a combination of fetch cycle plus execute cycle. So, in this way the whole instruction is represented by the combination of fetch cycle, that is FC, and execute cycle, that is EC. Now, it matters that what are the T states involved in the fetch cycle and what are the number of T states involved in execution cycle. They may vary depending upon the instruction. So, this is pictorially represented here, like instruction cycle is a combination of machine cycles and each machine cycle is a combination of different states. They can vary from 3 states to 6 states and all. So, these are the very basic machine cycles as I have already discussed. Now, we will discuss one by one. Opcode fetch machine cycle. The first step of executing any instruction is the opcode fetch cycle. In this cycle, microprocessor brings in the instructions opcode from the memory. So, here the memory operation is taking place and it is obviously the read operation. So, and opcode fetch machine cycle is represented by the status signals S1 and S0 equal to 1 and 1. So, this machine cycle is having the 4 T states and uses the first 3 T states to fetch the opcode, and the 4th state is used to decode and execute it. Now, how it is represented, let us see. So, this is the clock representation of the T states. Now, the higher order address bus, that is A8 to A15, is represented by this. It is latched in the first T state itself and will be latched till the last T state. Lower order multiplexed address and data bus is latched, that is a lower order address bus is latched in the first T state, and during the latching of the lower order address bus, this ALE signal goes high. So, ALE signal is used to demultiplex the lower order address bus from the multiplexed address and data bus. So, the latching of the lower order address bus is represented by the ALE signal going high. In the later part, that is from the T2 state, the data bus, lower order data bus is latched here till the next state. So, now after the first state, ALE signal goes low. It means that the address bus has been delatched now. Now, input output oblique memory bar and S1 and S0 signals are represented by the combination of these group of signals. So, input output memory bar should be 0 in this situation because this is the memory operation, and during the opcode fetch cycle S1 and S0 are both 1 1. So, this is the representation of the group of signals. Like, what are the signals involved in this group? Input output oblique memory bar S1 and S0. Now, we talk about the read signal. since this is read operation, memory read operation, and it is being executed in the second state when the data bus carries the signal. So during this state, the read signal is activated by asserting it low, because this is active low signal. So in this way, these signals, that is the clock cycles, the T states, address and data bus, ALE, input output oblique memory bar, S1 and S0, and read signal. So control signals is this, and these are the status signals. All these signals represents the graphical, gives the graphical representation of the fetch, opcode fetch machine cycle. So now we talk about the memory read machine cycle. Again, this cycle is executed to read the data byte from the memory or to fetch operand in the multi-byte instruction. So here again, this is the memory operation. So input output oblique memory bar goes low to represent the activation of the memory part. S1 and S0 goes 1 and 0 respectively during the memory read operation. Write is 1 and read is 0, because read is active low. It has 3 T states. So let us understand what are these states, how these states are represented. But before going into that, let us first make it clear that during the execution of instruction which is involved in machine read cycle, that is memory read cycle, the very first instruction, very first machine cycle is always opcode fetch. So whenever an instruction having the memory read machine cycle is represented, first of all the opcode fetch machine cycle will be shown, and after that memory read machine cycle will be shown. But since we have already discussed the opcode fetch machine cycle, so in the subsequent slide I am not showing the opcode fetch machine cycle, I am showing only memory read machine cycle. So basically 4 T states are included in the opcode fetch cycle and 3 T states are included in memory read cycle, making it total 7 T states. Let us have a look on this. This is the T states. This is the higher order address bus, which is latched in the first T state itself and goes till the last T state. Lower order address bus is latched in the first T state, and after that, after this gap, this is the tri-state, and after this the data bus is latched. Lower order data bus, that is D0 to D7, is latched during the later half of T2 cycle and goes till the T3 cycle. Now this is the ALE signal. The ALE signal represents the demultiplexing of the lower order address bus, which is done in the only in the first state, that is T1 state. So during this state ALE goes high, and again after this it goes low. Now we talk about the status signals. This line represents the combination, the group of the status signals, in which input output oblique memory bar is represented by 0, because this is the memory operation. S1 is given by 1 and S0 is shown by 0. Now the read signal is represented by the read signal asserted low, because this is active low signal during the read operation. So in this way, this completes the timing diagram of memory read operation. Now we talk about the memory write operation. So this is executed by the processor to write the data byte in the memory location, and it is exactly the same as the memory read operation, that is memory operation is there, so it will be 0. S1 is 0 and S0 is 1, that is the memory read operation. Yes, and write is 0 and read is 1, and it has only 3 T states. Let us see. So in this way the clock is represented here. Again the higher order address bus is latched from T1 state, goes till the last state. Lower order address and data bus is multiplexed, and using the ALE signal the lower order address bus is demultiplexed from this group of signals, and it is demultiplexed during the first T state, during which the lower order address is latched during the and during this operation the ALE signal goes high. After this is the tri-state, and then the data lower order data bus is latched during the later part of the T2 state, and it goes it remains latched till the end of T3 state. Now we talk about the status signals here. These are the status signals: input output oblique memory bar, S1 and S0. Since this is the memory operation, it goes low. S1 is 0 and S0 is 1 in the case of read operation. So again we talk about the write operation. Since this is not the read operation, this is the memory write operation. So, here we are representing only the write signal, not the read signal. So, the representation of read signal is given by asserting it as low during the later part of the T2 state, during which the data bus is carrying the data. Now, we talk about the input output read machine cycle during this state. So, since this is the input output operation and it should be 1 here. So, S0 and S1 is 1, 0 and 1, and write operation is 1 and read is 0, because these are active low signals. So, let us have a look on the timing diagram of the input output read operation. This is the clock cycle, this is A0, and this is the higher order address and data bus, and it is carrying the port address and which is latched during the T1 state. Lower order address and data bus is multiplexed, and to demultiplex the lower order address bus, in order to carry the input output port address, the ALE signal should go high, which is going high in the T1 state. During the T1 state, this input lower order address to hold the input output port address is latched, that is that it is demultiplexed and it is latched during the T1 state. Now after this it goes into tri state, and during the later part of the T2 state, again the lower order data bus is latched. Now we talk about the status signals. So, the input output oblique memory bar is represented by 1 since it is the input output operation. Now, S1 and S0 is represented by 1 and 0 since it is the input output read operation. Now, since this is the read operation, we are representing only the read control signal, not the write control signal. Since the reading of the data is taking place during the later part of the T2 state, so during this time this is asserted low, since this is active low signal. Now, we come to the input output write machine cycle. Again all the instructions are same except this read write signal which is changed, and during this S1 and S0 are also changed. So, let us see that these are the representation of the clock signals. Now, higher order address bus is carrying the port address and which is latched during the T1 state. Lower order address bus is latched during the T1 state and it goes tri stated here, and during the later part of the T2 state, this multiplexed address and data bus is used to carry the data, and so the lower order data bus is latched. The ALE signal goes high during the T1 state when the lower order address bus is latched. We are representing the write signal here, and the write operation is taking place in the T2 state. So, here this write signal is asserted low to represent the activation. Input output oblique memory bar S1 and S0 are represented in group to represent all the status signals. So, input output oblique memory bar is 1 in this case, since this is the input output operation. S1 and S0 goes 0 and 1 respectively. So, here I have considered an example here. So, let us understand all the machine cycles with an example. So, I have taken the instruction MVI B, 05H. So, the opcodes for the MVI B, 05H are 06 and 05. So, this 05 is the operand and 06 is the opcode for this instruction. Now, I assume that opcode is lying at the memory location 1000H and the operand is stored at the memory location 1001H. Now, since in this instruction I have to understand that which machine cycles are involved. So, the very first machine cycle is always opcode fetch. Next machine cycle, since this data is being read and being copied to the register B, so this is the memory read operation. So, the two machine cycles are used in this instruction, that is the opcode fetch machine cycle, and the second machine cycle is memory read. So, the opcode fetch machine cycle is using 4 T states and memory read machine cycle is using 3 T states. So, let us understand what is happening during the opcode fetch machine cycle. So, this is the T states representation here. Input output oblique memory bar S1 S0 are represented using the group signals, and this is the memory read operation. So, input output oblique memory bar goes low. S1 and S0 both are 1 1 during the opcode fetch machine cycle. the higher order address bus is latched during the T1 state, and this higher order machine cycle is carrying the higher order address. What is the higher order address? This one, 10 of opcode fetch part. So 10 is carried by this higher order address bus, and the lower order address bus is multiplexed during the T1 state, and it is carrying the lower order address, this 00 part, last part. So in this way, so this last part is carried by this lower order address bus. So, and during the latching of the lower order address bus, ALE goes high here, and in the later part of the T2 state, this multiplexed address and data bus is used to carry the data. What is the data here? Data is this opcode. Opcode is the data for the data bus. So here the opcode is being fetched, so this is the data, and during the reading of the opcode from the memory, the read signal should be activated. So it goes at logic 0 during this, because this is active low signal. Now we come to the memory read operation. So now the memory locations considered are 1001 and the operand is 05H. So during this, since this is again the memory read operation, so memory input output oblique memory bar is equal to 0, and S1 and S0 are represented by 1 and 0 to indicate the read operation. Now the higher order address is latched during this T1 state of memory read cycle. So higher order address is 10, lower order address is 01 here, and this is latched during the T1 state of memory read cycle, and during the latching of the lower order address, ALE signal goes high. So it goes high here. Now during the reading of the data from the memory, again the reading operation is activated, and this is represented by active low at represented by the logic low at read signal. So in this way, this completes the timing diagram of this instruction MVI B, 05H. So whichever instruction is given to us as a question in the question paper, so how we will solve it? We have to understand that what is the length of the instruction. So we have to get ourselves clarified with the instruction format. Then we have to understand what all the machine cycles are involved in the execution of this given instruction. So we have to mention the instruction machine cycles involved in this instruction. Then we have to assume that suppose the opcodes are, which opcodes are located at what location. So since this is the 2-byte instruction, 06 is the first byte and 05 is the second byte. So first byte is located at this location and second byte is located in the another consecutive location. So in this way we have to make a format, then we have to proceed with the timing diagram. So this is the way of solving, this is the explanation for this instruction. That's all from my side on the timing diagram. I hope the timing diagrams are clarified to you and you can clearly make the timing diagram for any instruction given. Thank you for today's lecture.